We're going to continue chapter 16 with preparation of alcohols from epoxides. So these are some new reactions in which you can make an alcohol. This one, you're going to use a Grignard reagent or an organolithium compound, react it with ethylene oxide, which is a epoxide compound. And basically what that's going to do is going to add 2 additional carbons to your carbon chain of your alcohol. And you'll end up making a primary alcohol. So in general, you'll get your Grignard reagent, your ethylene oxide, or your 1,2-epoxy ethane, in the presence of diethyl ether and an acid catalyst, in this case the hydronium ion, and you'll make your primary alcohol. So you can also do this with an organolithium compound instead of the Grignard reagent. This is just showing you the process. So here we have our Grignard reagent. Our R group, our bond here that's attaching our magnesium iodide to our alkyl group, is going to break. The alkyl group's going to combine with one of the carbons of the ethylene oxide. This bond is going to break and open the carbon chain. You'll temporarily add on the magnesium iodide or whatever it is. Then you'll use your hydronium ion to replace that with a hydrogen, and you'll get water as a byproduct. So here's a more specific example with using alkyl chain. So here we've got a 6-carbon alkyl chain with our Grignard reagent, or in our Grignard reagent. It's going to react with our ethylene oxide. You're going to end up breaking the bond here. Remember, this R group is going to attach to one or the other of these carbon groups. The bond is going to open here, and our OH group is going to be on this one, so we'd add 2 additional carbons to our 6-carbon alkyl chain to make an 8-carbon primary alcohol. So just looking at an example, it says each of the following alcohols has been prepared by a reaction of a Grignard reagent with ethylene oxide. Select the appropriate Grignard reagent in each case. So if this is our final alcohol, we know that these 2 carbons right here are going to come from our ethylene oxide. So we'd break it here, and then we'd add on our magnesium bromide or whatever we want to use as our Grignard reagent. So this will be our Grignard reagent for this first product. For this product, again, here's our 2 ethyl, our ethyl group, or our 2 carbon group. So we again break here, and then our magnesium bromide or magnesium halide would attach to our cyclohexane. The next reaction we're going to look at is preparing diols. A diol is a compound that contains 2 OH groups in the compound. In this particular case, if you have 2 carbonyl groups, you can use a reaction to make an alcohol. So if we have a hydrogenation of a dialdehyde using our hydrogen and our platinum, then we're going to reduce our hydrogens. Have a little help here with my kitty cat friend. I'm going to reduce my aldehydes or my carbonyl carbons to our OH groups. So example here is a dialdehyde. So you have an aldehyde group on both ends. You'll use your hydrogen, and in this case nickel we used. Or you could have used your sodium borohydride complex that we talked about earlier, or even our lithium aluminum hydride. So you can use any of these reduction processes that we did. And what that's going to do is going to reduce the carbonyl carbons down to OH groups. When you name a diol, you're going to find your longest consecutive carbon chain that has the 2 OH groups. That's going to be our parent chain. You keep the entire name. So if you have a 5-carbon chain, in this case it would be pentane, so you don't take the E off like we did some other time. And then we add diol at the end, and then in the front of that you have to indicate the numbers where these OH groups are, or you could break it and put it before the diol. For the aldehydes, if you have a dialdehyde, then you're simply going to change it to a dial at the end, but everything else is just like the diol. Another reaction that we have is a hydroxylation of an alkene, and what this is going to do is it's going to make a vicinal dihalide, a vicinal diol, meaning that you're going to have your OH groups on adjacent carbons. One of the most familiar vicinal diols is ethylene glycol. So you'd have your OH on adjacent carbons, but you have others as well that you can see. In this, you're going to use osmium tetroxide. You'll start off with an alkene. You use osmium tetroxide. It's going to make an intermediate complex that's going to be a cyclic osmate ester, so you can kind of see this in the next slide here. Don't get too bogged down in that. Then you're going to use as an oxidizing agent our tertiary butyl hydroperoxide, which is this compound, and a basic solution. So basically, taking all those things together, you're going to end up going from an alkene to a diol using osmium tetroxide, your water, or you could use any of these reagents here. So here's an example. Here's our alkene. So these two carbons are where we're going to put on our adjacent OH groups. That's our oxidizing agent. This is our osmium tetroxide, alcohol, base. So you'll take all of those and then you'll add on your OH groups on adjacent carbons. This is a form of syn addition, so they do attack the same surface or the same plane of the double bond. So if you do have an alkene that is in a cyclic pattern, then that will affect its stereochemistry. So here's an example. If we have this alkene and we use the osmium tetroxide and so forth, then you can see that our OH groups both have to be in the down position because they both attack the carbon on the same plane of the double bond plane. Now the next thing we're going to look at is just a quick review on some reactions of aldehydes. So these are the reactions that we have done in the past. Now we didn't do the very last one, which is actually out of chapter 8, but we will look at the other ones and just a quick review. I wrote them out in hand just so it'll be easier to read my scribbling. But the first one is going to be your reaction with a hydrogen halide. So this was the ones we talked about with SN1, SN2 mechanism in chapter 4. You'll take your alcohol, react it with your hydrogen halide. You'll get an alkyl halide and water. If you start off with a tertiary alcohol, remember you're going to use hydrogen chloride, which is a less reactive hydrogen halide, to make a tertiary alkyl chloride. Start off with a primary alcohol, you'll need to use a more reactive hydrogen halide or the hydrogen bromide. You'll make a primary alkyl bromide. Secondary alcohols can use either one. It kind of depends on which mechanism it'll use, depends on which solvent you end up using. For the second reaction, they talk about a reaction with thionyl chloride. So again, your alcohol, this can be any class of alcohol, reacts with thionyl chloride, which is our SOCl2. You're going to get a alkyl halide again. So in this case, it'll be a alkyl chloride because you're going to use the chlorine from the thionyl chloride, then sulfur dioxide, and then your hydrogen chloride. Now the reason that this reaction is helpful is because we can't make a primary alkyl chloride using this particular process, so this allows us to make a primary alkyl chloride if we need to. This one is a reaction with the phosphorus tribromide. Again, you're going to make an alkyl halide, this time an alkyl bromide. If you start off with your alcohol, you're going to use our phosphorus tribromide, which is our phosphorus and 3 bromines here. You'll make your alkyl bromide and your phosphorus acid only, of course, if you use 3 moles of the alcohol, which will make 3 moles of the alkyl halide. This particular reaction is especially helpful if you want to make a tertiary alkyl bromide, because we can't make one up here because the hydrogen bromide is too reactive. So this gives us an opportunity or a way to make a tertiary alkyl bromide. This one is you're starting off with an alcohol, so you're going to do a dehydration of alcohol using an acid catalyst. Remember, our acid catalyst can be sulfuric acid, phosphoric acid, or potassium hydrogen sulfate in the presence of heat. This will be our alpha carbon that has an OH on it. Our beta carbon will be an adjacent carbon. It will follow the Zetsif rule, so whichever of the carbons has the fewest number of hydrogens or the most substitutions is going to be the direction the double bond would form to make the major product if you had some regioselectivity involved. So here's our alkene. And of course, it's dehydrating, so water is a byproduct. The last one, probably don't see that one a whole lot, but it's a conversion of a para-toluene sulfonate ester to make a, in this case, you're going to make a compound that has the parasulfonate ion attached to it with the alkyl group now. So you're going to take your alcohol, break off the H or the hydrogen. Your para-toluene sulfonate halide is going to have, in the place of this X, either chlorine or bromine. You'll break that off, so you'll get hydrogen, chlorine, or hydrogen bromide as a byproduct, and then your R group is going to attach, or your OR group is going to attach here. So you can see that this comes from my original alcohol. So this makes a para-toluene sulfonate ester. Sulfonate ester being this grouping in here. So we're going to look at one new reaction on this PowerPoint, and then I'll do a next PowerPoint to do some of the additional reactions. So this first one is a conversion of alcohols to ethers, and this one is going to require 2 moles of a primary alcohol, and you'll make a dialkyl ether. So both R groups are going to come from the same alcohol, so both R groups on either side of the oxygen and the ether are going to be identical. So in this particular case, if I have 2 moles of this particular alcohol, then this functional group is going to be on one side of the oxygen. You'll have an additional one on the opposite side as well. You do use an acid catalyst in this process in the presence of heat. So if we're looking in general at this, if these are my 2 alcohols, one bond is going to break here at the hydrogen. The other one's going to break at the OH group. That's going to give you your water, and then this oxygen is going to link up to the carbon of the other to form our ether. If you do a condensation reaction, which this is an example of, you're going to have 2 molecules or products breaking down to form one larger molecule. So this is an example of a condensation. You might have heard that in a biology class or something. So in this particular one, we have a 4 carbon alcohol. We'll use our acid catalyst in the presence of heat. So you'll have a 4 carbon group on one side of the oxygen, a 4 carbon group on the other side of the oxygen. Now there's 2 ways to name ethers. One way is the functional way. So in this particular case, if I have the same functional group on either side, I'm going to call them a dibutyl group, and then I put the word ether at the end. So that's a dibutyl ether. If they hadn't been identical, as we'll see later on with other types of reactions, then you would, this kind of depends. Sometimes you do the shortest chain first, then the longer chain. Other books will do it alphabetically. So we'll look at that one in our nomenclature in our last PowerPoints. Now our substitutive name, you're going to use a alkoxy name. So one functional group, in this case since they're the same, it won't matter, but it'll be butoxy, and then you'd name butane. So you're going to name the longest, typically the longest carbon chain is the parent, and then the alkoxy part is going to be the shorter. In this case, it won't affect it because they're both going to be the same length for this particular kind of a reaction. This just kind of goes over the mechanism, so you can kind of see they're similar to some things we've done in the past. So the first step, starting off with our alcohol in the presence of our sulfuric acid, you're going to do a protonation step and form an alkyloxonium ion. We're going to form this as an ion that will reform later on because it's just serving as a catalyst. The second step is the nucleophilic attack of the alcohol. So the alcohol is going to attach to the carbon of the original alcohol. So it'll attach here, and then this bond will break off and liberate the water molecule. So we're going to have this complex. So now you've got your oxygens connected to carbons, and then all we got to do now is get rid of this hydrogen. So the last step then is a deprotonation step. This is when your ion that you formed in the very first step, this one right here, is going to come back in and pick up that hydrogen, reform the acid, and then of course you'll form your ether. Now this is kind of a unique reaction. This is the formation of a cyclic ether from a 5 or 6 carbon diol. So if you have this will only occur with 5 or 6 membered rings, so you can't do it with smaller or larger ones. But if you have a 5 carbon chain, so this is 1, 2, 3, 4, 5, or even a 6 carbon chain, you can do this. If it's a diol, you'll react it here. It's going to show you what's going to happen here. So the OH group of one end, these electrons are going to shift over and create the side of this ring. This bond right here is going to break off and produce electrons on the water molecule, and you'll end up forming this molecule. So again, 5 or 6 carbon rings allow you to form a ring-shaped ether molecule.